In this tutorial, we are going to optimize this parameterized heat-sink model, where our fins here, the width, thickness, and length, are our design variables. And the simulation done here is a thermal simulation where our cylinder will conduct heat, and we are going to use our fins to dissipate this heat here. To create the optimization, we are going to use our parameterized geometry inside of Inspire, the connection between SimLab and Inspire to create the thermal solution and the automated process, and then our optimization in HyperStudy. This is the general workflow for SimLab. First, we are going to record our script where we are going to import our model, create the mesh, set our loads and boundary conditions, create our response, solving our heat transfer solution, export our response and saving it in the same folder as our script, and finally saving our script, exporting the parameter file which we will need to manually set up our HyperStudy setup. First, we are going to create our script. For this, on a folder, let's have the necessary files to create the script. In this case, we'll use our CAD model, which has all the design variables in it, and a material template. So let's go back to SimLab, and here, under Automation, Scripting, let's set our working folder. In this case, we'll use the same folder where we already have our necessary files. Then, again, under Automation, Scripting, Record. Here we'll see that it started to record our script. So each step that we create or use, it will record it as a Python code. So the first thing is to go under File, Import, Database. On the folder that we just create and have the files, we're going to import this heatsink stmode database. In this case, because we are using Inspire. If you're using CATIA, Creo, NX, or any other CAD software, you will need to import it as a CAD. So let's open this. Okay, once we imported our geometry, there is different ways to see if the design variables are working. The first one is right-clicking under the assembly name. We have this regenerate button, and here we'll see our design variables. We can also set the new values for the geometry so that it connects to our CAD software and changes it. In this case, we have three simple variables: the width, the height, and the thickness of our fins that you can see on this dark green color. Just going to set cancel. Another way to see if they were imported is under our parameter browser right here. We can also see our CAD parameters. Okay. So now we're going to start to set up our solution. For this, first we are going to select our fin faces here, right-click, and under Select Associated, click on Entities. This is to create a group that contains all of the faces from our fin's body here. So let's just rename it as fin faces. This is important because when recording a script, we don't want to directly select the faces, because if we do this, this is just as an example, we are selecting a face ID. and these IDs can change depending on the mesh, on re-importing a CAD, and so on. So this will make sure that every time that we run our script, it will remain the same. So for this, we are going to use groups and create groups on a different way, because when selecting the group, you can see it will select the name of the group directly, or it will look for the group, so we won't have that problem anymore. Okay. Now that we created our fin face group, we are going to join our fin face and this support here on with light green color. So for this, let's go to the geometry ribbon, connect, boolean, and here our input is our cat parasolid, and we are going to combine our fin body here and our support body. Okay, make sure to have this create connected bodies deselected because we want to merge them. Okay, there we go. So now we have only one body. Now we can do our surface mesh or 2D mesh. For this, we're going to use first order trees, and we are going to select all of the bodies here. You can do Ctrl+A on the 3D window, or just select here the assembly name. And to create the mesh, we are going to use the thickness of our fin here. So for this, you can right click on the average element size and do select parameters. Then it will open our design variables here, select the one that we want. For this, we want to make sure to have at least two elements here on our thickness. So we are going to divide our thickness by 2, and we want to drive the same design parameter for our minimum element size and our curvature minimum element size here. So for this, I'm just going to copy paste here this one divided by 10 our average element size, and for our curvature by 4. Okay, I'm also going to leave our identify features and mesh on cat body enabled and just mesh it. Okay, now that we have our mesh body here, if we look into our face groups and select it, you'll see that it will select on the fins that is our cat, not our meshed body here, right? Because we created that group on our cat body. So what we're going to do is that we're going to transfer. So right click on the group, transfer. We're going to transfer our cat groups to our mesh, right? So for this, you have to enable or view all of the bodies here. So I want to transfer from my fins cat group to our mesh. Okay. Now I can hide our cat bot here. And if I go back, we'll see there is a new group created called fin faces and SM for surface mesh. So if I select it, you can see it select our fin faces from the surface mesh here. Okay. Now we're going to need another group, set it as our boundary condition. So for this, I'm going to select here my cylinder, right click, select features, and I'm going to use here the fillet radius based feature. So it will look for all of the fillets that are between 60 and 65 millimeters. So which is basically this inner of cylinder, let's say. And I want to create a group out of it, which I'll just call flux. Okay, and there we go. It will look for all the features that apply the radius-based feature, and there we go. Okay. So now that we created all of our groups. Let's just review they are correct. So for this, I'm just going to select first the thin faces from the surface mesh. This is correct. This is going to be our convection boundary condition, and the flux is this one. Okay. So now I'm going to create a mesh control, a volume layer mesh control here, selecting the face. So I'm interested that my volume layer from the thin faces also has 2 layers between it. So I'm going to select face here as my input, select my group thin faces, and having 2 number of TET layers. Okay, there we go. So now that we have our mesh controls created, we can do our volume mesh, in this case our TET mesh. So again, I can go here under my assembly browser, select the assembly here to select all of the bodies, and this is also going to be driven by our thickness here. So let's just select our parameter. Remember, right click, select parameter, and I'm going to divide this by 2 again. Okay. The quality, I'm going to change it from skew to stretch, and okay. Here, make sure also to have replaced the mesh in existing model to make sure that our groups here created will apply on our volume mesh. Okay, with our volume mesh done, we can now create our heat transfer solution. So for this, I'm going back to Solutions ribbon here. Under Thermal Heat Transfer Analysis, a OptiStroke Steady State Heat Transfer Solution. I'm going to select our assembly name here, and OK. Perfect. Now we created our heat transfer solution. So the next thing is we're going to set our materials. So for this, under the property browser, I'm going to first delete all of the default materials here, and then again right click on the materials, and I'm going to import the template, our heatsink material template here. So now we have a aluminum, copper, and insulator material. Now what I'm going to do is to set our materials here. If, for example, you want to use the materials tab here and organize it a little bit better, you can just do name, right click under name, and disable the ones that you're not interested in. This is not going to be recorded recorded on our script, so there's not problem of changing things here inside. So now I can just set our materials. So for our thin faces here, I can do aluminum. For the insulator, which is body 1, I'm going to use our insulator material, and for our cylinder here, copper. Okay, so now our materials are set. So we can first change our unit system here from millimeters to MKS to meters. Then we can set our first boundary conditions or our load and constraint here. So the first one is flux. I'll go to our group browser and select the group we created using the select features here of flux, and set it as 300 watts per square meter. Okay. Then I'll create our convection constraint. For this, I'll select thin faces surface mesh, set the temperature to 300.15 and fill coefficient to 1. Okay. Then we already have our loads and constraints. The next step is to set our contacts between our bodies here. So contact, I'm going to use auto contact. And first I'll set my contact type as tie. Then as main body, I'm going to use first the insulator here and secondary body the fins. I'll set apply. And the last one is main body fins and our secondary body copper. Well, our cylinder. And then the same contact type and OK. So now that we have created our contacts here, we're going to need a response. So this response will tell us any results that we're interested in after to optimize or to have it as a control. So right click on the results and we'll find this response here. And in this case, I'm interested in the temperature. I'll select which entities I'm interested in. In this case, it is the fin faces. Then I'll just change the value to average and create. Okay, so if I go back here to my solution browser, I'll see here a response from the temperature. Now we can set our the numbers of processors to solve our solution. So for this, I'm just right-clicking on Settings, Format and Execute Options, and here I can set the number of processors. Remember that when using HyperStudy, you can also set how many simultaneous runs you want to do. So be careful on how many processors you set here, and because if you have many simultaneous runs with many processors, you could go way up to your hardware's capabilities. Okay, so I'll just set it up as 4 here. Okay. Now that we have everything prepared, we're going to save our database. So Control S, and we can name it as HS for a heatsink solution. Okay, there we go. We saved our database. So now we can solve it. So on the results, right click, update. Once it's finished solving, we can export our response. So for this, on our solution name heat transfer, right click, then export responses. Here we will set a name to save it. Then let's go under automation, scripting, stop to save our script. Before jumping to HyperStudy, we need to organize our files. So for this, I created 2 new folders. One where we'll save the minimum amount of files to create and set up our study, and the second one where we will save our study made. So let's go to our script creation folder, and here we'll copy all of the necessary files for the setup. So the first one will be our script. To run the script, we need our CAD file and our material template. And specifically for HyperStudy, we also need to give him a parameter file. So this parameter file, you'll find it wherever you saved your script. Let's then copy and paste it in our newly created folder. And here the very first thing to do is to change our parameter file, because HyperStudy will look for this file with a specific name, which will be first the name of the folder. So in this specific case, HS files on dash params. So this way HyperStudy will be able to find and import the parameter. If we open up our file here, we'll see all of the parameters created inside of SimLab. The ones that we're interested in are these here under model, where we'll see our parameters created: the width, the height, and the thickness. They are all type real. You could also have type length or any other type like this, and the value. So now let's refine our script. So let's open up the HS script file. Now we can see how our script works. So we'll find all of the functions we use to create our script. So the first one to import our CAD model using this Inspire database import. Here we'll also find a really important part of our scripts, which is how our paths are defined. In this example, we see a relative path with this / symbols, which means that it will look for our heatsink st-mode file in the same folder where our script is saved. So this is really important to always take into consideration, because if our model is not present in the same folder in this example, it will fail to import it and the rest of the script won't work. Okay, so now I'm jumping to another section, which is the material creation. Here we will see that we have two options. First, we are creating our materials, our copper insulator, and here we can see we'll have two options. One is to leave. Here we see we have two options. The first one, if I open this function here, you'll see that it creates our aluminum material with all of the properties necessary. The same thing it does for the other two materials. But we also have our import the material template function. So here we can decide whether we want to erase the import material template, which means we won't be using this .xml file anymore because our script will handle the creation of the material, or we can eliminate the material creation. As you can see, uses a ton of lines here to create because of all the properties necessary to define it, and just leave our template. So this is what we'll do for this exercise. We are just going to erase the material creation. Now we can set up our study. So for this first, let's go to Edit, Register Solver Script, and make sure that here we have selected our simlab.bat file. So normally you can find it on this path here. So under Altair, the version of SimLab you're using, SimLab bin Windows 64 and simlab.bat. Okay. Now let's create the new study. Here, let's set the location. So I'm using this folder we created before. Select folder. Okay. And here, now we can add our model. So add model, SimLab. Okay. And on the resource, we are going to set our Python script. So let's select our folder here, jump one back, and select the folder where we have the minimum amount of files. It's important like this because HyperStudy will copy and paste all of the files that are present in this specific folder. Okay, there we go. So once we have set our script here, let's import our variables. Next, here we can see here you can change your intervals or your lower and upper bounds from each of your design variables. In this case, we are going to leave them as default. Next, And here we are going to test our model. So the script we just set, select run definition. So once it finished testing our script here, let's jump to our define output response section. And from here, let's go to directory browser. Let's open approaches, setup, run, M1, HS files, and here let's drag and drop our SimLab response file. This will open a new window here. Let's just go to next. We are going to use the very first option here, next. And here, let's highlight our value, just the value. Then do right click and select value. This way, each time it will look for our response, it will look for the specific value given here. So next. Here we can change the label or the name for our response. I'll set it up as heat transfer temperature. You can set it up to any name you want. Okay, let's put finish. And here, let's just evaluate it. And we can see we have 343 kelvins. Okay. Let's go back to our Explorer browser, and before doing our DOE, here on goals, let's select this plus sign, and because we already know how we want to optimize our model, let's change the type to maximize. So our goal will be to maximize our temperature on our fin faces. Okay? And now on our Explorer browser, let's do right click, add, DOE, and from definition from our setup. Okay. From here we are jumping directly to the specification section, and we are changing our mode to Sobol, because Sobol will evenly space our points of the DOE in our design space. This way we will get a more precise and exact fit model afterwards using the data we are going to get from our DOE here, and this way replace the solver using only our new mathematical model. Okay, so we can apply this and jump to the evaluate section. Here the first one is this evaluation task, where once we start to run everything, we will see if it successfully wrote and executed each of the runs. Then if you want to see the values proposed by our mode, you can see it right here. You can also edit the matrix here, so you can run the matrix and just add some runs or edit the ones that you want. But by default, this will already give us a really good points here to work with afterwards and get our fit model. And before executing here, we are also going to change this multi-execution to just one job. So basically we are sequentially running each run after the other. We recommend this when using the connection from a CAD with SimLab. So for example, now that we are using Inspire with SimLab, it is better to run one after the others rather than having a lot of them run at the same time. Okay, I'll stop the recording because the DOE will take some time. Now that the DOE finished all of its runs, we can see if first they were all successful. We can also see here on the evaluation data the response, the value of the response from the temperature for each run. In case one of the runs wasn't successful, you can deactivate the ones that were, and then just reevaluate those that failed. So with all of this information, now we can train our mathematical model with a fit function. So For this, on the Explorer browser, right-click, add. Using this fit existing data, we can select our definition from the DOE, for example, and just set OK. Now we can jump to our specification section. And here first, we need to set our origin settings, right? So we are going to use the values and all of the information created from our DOE. You can also display or view all of the data here. So you can see again all of the runs with its respective responses. Okay. So we just set it to apply. We are also going to leave this fit type as fast. So it would automatically select the best mathematical model for our values here. Let's go to evaluate. We're just evaluating the tasks, and there we go. So now we already have our mathematical model, and we don't need to solve every time with our solver each simulation. Here, quickly on our post-processing section, we can see the diagnostics here and see the correlation. So this will tell us how good our mathematical model is with respect of the simulation done by our solver. Okay, so now let's create our optimization. So again, let's go back to our Explorer browser, right-click, add, optimization, definition from our fit model, and okay. So before going to specifications, let's jump to our define output responses, because here we are going to change the evaluate from expression, which would be with our solver, to our fit model. So now we are going to use our mathematical model done before. Now let's go to specification. And here we are also going to change the mode to the global response search method. We recommend this because it will explore our design space on a global level, and it requires less iterations. Okay, so let's apply this, then go to evaluate, and also evaluate all of the tasks. Okay, so now that it finished the evaluating all of our tasks here, we can also see on the iteration plot how quickly it reached to our goal. So we can actually see on the very first iterations, it almost already reached our goals here. Then on our post-processing side, we can see our optimal point in our design space here on this Optima section. And if you want to specifically see the iterations, you can open this show iterations, and it will show you the values needed for this optimization part. Another way of visualizing this again is on our evaluate section. Under evaluation data, you can see all of the evaluations done and specifically see which is our optimal values here.